Hello, students. Today we'll be working on your last lesson of the semester. So we're tying everything together and working on a final analysis of the graph of a function. So you'll see that your first four items are really pre-calculus items, and you'll do those just hopefully without too much other instruction. I have some hints for you on the back when we go through your example. I will note on number 4 that you only need to do this if you have a rational function. So if the function is a fraction, you need to look for asymptotes. You know to look for a vertical asymptote where the denominator is 0. You have this from our last lesson on horizontal asymptotes. And this is something that we haven't done yet this year. We'll look at the example on the back. We'll have a slant asymptote, and this is only when there are no horizontal asymptotes do you have to check for a slant. Steps 5 and 6 are for your calculus analysis. So looking at the derivative and finding where the function's increasing or decreasing, having maxes and mins, and the second derivative looking for concavity and the points of inflection. When all that is said and done, I think the thing that you'll want to know in creating your table is to make your intervals. You'll use your critical numbers, your possible points of inflection, and the vertical asymptotes, only the vertical ones. And that will establish your intervals when you do your table. So we're going to move to the back and start working on your first example. So you have the function y equals x to the third over x to the second minus 9. So for your x-intercept, it says to let y equal 0. So we would say 0 equals x to the third over x to the second minus 9. And remember, that just means we need to set your numerator equal to 0 and do the cube root of each side, and we get x equals 0. So we have an x-intercept of 0, 0. And then your y-intercept, to do the y-intercept, you let the x be 0, so y would equal 0 to the third over 0 squared minus 9. And again, that's going to be a 0 over a negative 9, and that's going to be 0. So your x and y-intercept are both 0, 0. Sometimes you do have more than one x-intercept, but that is not the case for this problem. So I'm going to get rid of that work for your intercepts. Now we'll take a look at the vertical asymptotes for this graph. This would be for where your denominator is equal to 0. So we have x squared minus 9 equaling 0. We could have x squared equals 9 and square root, and we get x equals 3. That's one vertical asymptote. Remember, these are equations, so you should write them separately. X equals 3, x equals negative 3. And those will be part of your interval table. All right, then horizontal asymptotes. This is the lesson that we worked on last class. And you want to do the limit as x approaches both positive and negative infinity. We can see that we'll have the limit as x approaches infinity. We have the degree 3 in the numerator, so x to the third, and a degree of 2 in the denominator. So the higher degree in the numerator means that the limit does not exist. However, we can describe this as going to positive infinity. Now, as far as the horizontal asymptote, though, I would just like for you to write none. So it has no horizontal asymptote, so just write none. Now, because it does not have a horizontal asymptote, we do have to look for a slant asymptote. Whenever the degree is bigger by 1, causing you not to have a horizontal asymptote, then we have to check for a slant asymptote. We'll do that by doing long division. So I'm going to do that off to the side here. So this is to get the slant asymptote. We'll take your numerator, which was x to the third, and divide that by the denominator, x to the second minus 9. So what times x squared would give you x to the third? That's going to be an x, and that gives us x to the third minus 9x. And we can subtract, change the signs. This will cancel. We'll have 9x brought down. There is nothing that will multiply by x squared to give you 9x. So the 9x is the remainder. And the slant asymptote does not use the remainder. It uses the quotient. So the quotient is the x. And in fact, your slant asymptote is y equals the quotient. So y equals x. And don't be intimidated by that. Remember that that's just a line where your slope is a 1 and your y-intercept is a 0. So we'll be graphing that line as an asymptote for the graph. All right, so those take care of all of the pre-calculus parts of this analysis. And then your last 3 are your calculus parts of the analysis. And so we'll have to find the relative maxes and mins by doing the derivative and looking for the critical numbers. So I'll work on your derivative right here, f prime, and I'm going to have to write very small, trying to get it to where it doesn't look too distorted to you. So f prime would equal, now it is a quotient rule, so ho d high, all right, so that would be x squared minus 9 times the derivative of x to the third, which would be 3x squared, minus high d ho, so x to the third times the derivative of x squared minus 9, which would be 2x, and then your denominator, x squared minus 9 squared. All right, now you can multiply and combine like terms. So that would give me 3x to the fourth minus 27x to the second minus 2x to the fourth over the denominator of x squared minus 9 squared. And remember, we don't need to multiply out that denominator. And so f prime is going to equal, in your numerator, you'll have x to the fourth minus 27x squared. And in that denominator, you'll have x squared minus 9 quantity squared. Now, in order to work with that and simplify, I would strongly suggest that you think about factoring whenever you can on this. So you could take out an x squared and then have x squared minus 27 in your numerator. And then in your denominator, just leave it x squared minus 9. And then quantity squared. Okay, so there's your first derivative. And we'll have to use that to get our critical numbers. So I'm going to continue on with getting the critical numbers. So we'll set f prime equal to 0. Now, I would suggest you've got more space on your papers to work underneath where my work is. I think I'm going to work off to the side, but I would work underneath on the paper where you have space. So to get your critical numbers, I'm going to work over to the side here. Remember, we have to set f prime equal to 0. In this case, that would just be your numerator. So we'll have x squared times x squared minus 27 set equal to 0. So that means we can set each part equal to 0. So either x squared equals 0, square root both sides, we get x equals 0 as a critical number, or x squared minus 27 equals 0. So x squared could equal 27, and you could square root both sides, the square root of 27, which would simplify, and that is plus or minus. So plus or minus 3 square root 3. So you've got three critical numbers, 0 and positive or negative 3 square root 3. Remember to also set where f double prime is, where f prime is undefined. And that's going to be where the denominator, x squared minus 9 equals 0. Now, you should remember that we just did that. It's in green at the top where we worked on the vertical asymptotes. So we already know what's going on at 3 and negative 3. Yes, they are critical numbers, but they are already taken into consideration as being vertical asymptotes. So all of this work is for your first derivative, and you'll need that in order to establish the intervals. So now I'm going to switch and start working on the second derivative. So I'm going to erase the work that I had for the slant asymptote and start working on your second derivative. So for your second derivative, which would be for f double prime, so we'll continue on with the second derivative. So you want to do the derivative of the first derivative. And the form that I would use would be this one I'm circling in blue. you'd want to start with that, I think, for your second derivative. So f double prime will also be a quotient rule. And notice how you've got to be really careful with the first derivative because your second derivative depends on it. So it's Hody high, x squared minus 9 squared. And then the derivative of what we have in the numerator, 4x to the third minus 54x. So Hody high minus Heidi ho. So you have x to the fourth minus 27x squared. And then the derivative of your denominator, which now that's a chain. So you'll have 2, and then your x squared minus 9. And that will be to the first power. And then remember to do the derivative of the inside. So times 2x. And then all of this is over your denominator squared. So x squared minus 9 to the fourth power. So there's your second derivative line. And now I would encourage you to work on simplifying that. I'm going to do it by factoring. I'm going to factor out x squared minus 9 and then put a bracket to show what is left. So I still have an x squared minus 9 factor times my 4x to the third minus 54x. In the second part, though, the x squared minus 9 factored out. And so I have 4x. And then I still have the x to the fourth minus the 27x squared. And then the denominator, I have that x squared minus 9 to the fourth power. And I can do some canceling. So this will become a third power because this is going to cancel. So now we'll need to combine like terms. So doing a little multiplying. Oh, I canceled out the wrong piece. I couldn't see it. So let me correct that. This is still there. This is the piece that's canceled. Okay. So we're going to multiply these two together, and that will give us 4x to the fifth minus 54x to the third. And then minus 36x to the third. Plus 486x minus 4x to the fifth plus 108x to the third. Be really careful with your positives and negatives in that whole process. And then the denominator, x squared minus 9 to the third. Combine your like terms, and we'll have f double prime equaling, and unbelievably, things will cancel. You'll end up with 18x to the third plus 486x over your denominator of x squared minus 9 to the third power. And that 18 will factor out. In fact, 18x factors out. And then in parentheses, you would have x squared plus 27. And then your denominator, x squared minus 9 to the third power. So again, be very careful with your like terms because most often those will combine to something that will then factor out and make it possible for you to work with. All right, so now we've got a nice simplified version of the second derivative. And so again, I think you have space off to the side, but I need, oh, hang on here. I've started there. I need some space off to the side. So I'm going to do your possible points of inflection by setting f double prime equal to 0. And so we'll do that numerator, set that numerator equal to 0. Your numerator was 18x times x squared plus 27. And that means we'll set 18x equals 0, divide by 18, and we get x equals 0. Now, you've got 0 not only as a possible point of inflection, but on the left side of your screen, you'll see that 0 is also a critical number. So 0 cannot be both, so we'll have to look for what it really is by analyzing through the table. And then you've got x squared plus 27 equals 0. Hopefully you're recognizing that when you subtract that 27 over, you're going to get x squared equals a negative. In the real number system, we can't have that. So our only possible point of inflection will be this x equals 0. Remember that for f double prime undefined, we would set your denominator equal to 0, but we've already done that. X squared minus 9 equals 0. This would be the third time that we would have looked at that. We would get the 3 and the negative 3, and we already know that those are vertical asymptotes. So what you see on your screen would be all the calculus work for establishing the critical numbers and the possible points of inflection. And so now we're going to start working on the table. I'm going to start a new video to do that work.